Hi class, today we're studying the last section of chapter 1 that we will be doing. The section 1.8 is titled Higher Order Derivatives, and a higher order derivative is basically a derivative of a derivative. And the application is that if we're given a formula for distance, then we can find the derivative to find velocity, and then we find the derivative of velocity to find acceleration. So let's get started. If we have the function y is equal to f of x, the derivative, as we've been writing it, is y prime or f prime of x. Now you can take the derivative of that new function, so the derivative of y prime is y double prime. And the derivative of f prime is written as f double prime. This is called the second order derivative, or we just say second derivative. And if we have higher order derivatives, we could do triple prime or quadruple prime, but that gets really tedious to write like that. So we just replace that with numbers. And we'll see that as we go on. Now, I want to also talk about the Leibniz notation that we've been doing. And so if we had the first derivative, which is y prime, that was written as dy dx. But if you recall, that is d dx of the y equation or the y function. And so if we want to take a second derivative, we're going to take d dx of the derivative. So notice that here we have d dx of the derivative, which was dy dx. And when we write that, we write d squared y dx squared, because it's this portion that we do. It's the d dx that's done a second time on the function y. And so notice that notation is slightly different than what you might expect, but you have to pay careful attention to all of those notations and write it correctly. So just to go over some of the notation, if we are calling our function y, then the derivative is y prime, the second derivative is y double prime, and then the third derivative we write y with, it looks like a power, but to differentiate it from y cubed, we write y with a 3 in parentheses. And so that tells us that's the third derivative. And then this tells us it's a fourth derivative by putting the 4 in parentheses. And the 5 is the fifth derivative. And then this is the sixth derivative. If we're using function notation, and we're saying f of x, then we say f prime of x. Then we can also say f double prime of x. And then once again, just like the first notation, we start replacing with numbers. But notice that those numbers are in parentheses to differentiate between the third derivative of f and f cubed. And so we write it with this notation. If we're starting with y, then we can continue with Leibniz notation and say dy dx. Remember, that's d dx of y. So that's why the second derivative is d dx of d dx of y. And we would write it this way. Notice the placement of the 2's. And they're not in parentheses like we did over here. And so we'd write it this way. And if we take the derivative again, we change that to this notation, changing the 3 on the d and the 3 on the x. And then the fourth derivative, the fifth derivative, and the sixth derivative. You want to be comfortable seeing it in each different type of notation and also making sure that when you write it the correct way. So for video example 1, it's giving us an equation y is equal to 2 over x cubed, and it's asking us to find the second order derivative. First, let's go ahead and rewrite that equation. Rewriting it with exponents will help us find our derivative. And then let's find our first order derivative. So that would be dy dx, and that would be pulling down this negative 3 coefficient and subtracting 1 from it, so making it a negative 4. And if I want to simplify that, that's negative 6 x to the negative 4th. And then to write the second order derivative, we would write d dx squared, so to speak, of y for our second order derivative. And we're going to have the negative 6 coefficient. Then we'll bring down the negative 4. Subtract 1 from that, and we would get negative 5. Let's simplify that. Positive 24 x to the negative 5th. Let's just rewrite it one more time. And there you go. Notice for video example 2 that it looks like it's asking a different question because it's using different notation. However, it is the exact same question because it's still asking us to find the derivative and then to find the second derivative. Let's get started. Y prime, we have the chain rule in effect here, so we're going to do the outer part. We'll say 2 parentheses to the power of 1. And then inside my parentheses, I will put the inner function, 3x squared plus 1. And then I'm going to say multiply this by the derivative of the inner function. And so the derivative of this would be 3 times 2x to the first power. And so we can simplify that. Y prime is 2 times 3x squared plus 1 times 6x. Let's simplify it one more time. And we'll get 12x times 3x squared plus 1. Then to find the second derivative, or y double prime, we need to do the product rule. So that's the first times the derivative of the second, 3 times 2x to the power of 1 plus 0, plus the second times the derivative of the first. Let's simplify some of these parts, like the 3 times the 2x, and then let's pull that coefficient in front. Now in most questions, as soon as you simplify each part, you would pretty much be done, especially if there's binomials and then powers going on here. I don't want you to take the time to multiply it out. But because this question's fairly simple, I'm going to go ahead and simplify this. And so there's our two solutions, y prime and y double prime. Okay, moving on to video example 3, it's asking us to find the fourth order derivative. So our function is 1 over x, which we can just say is x to the negative 1 power. So d dx of x to the negative 1 power would be negative 1 x to the power of negative 2. Taking the derivative of this, we would write of x to the negative 1 is equal to negative 1 times negative 2 x to the power of negative 3. In other words, positive 2 x to the power of negative 3. Notice that the function inside our derivative doesn't change. This is the second derivative of our original equation. Now, I could also write that this is the first derivative of that equation. So it just matters which equation you're talking about and which second or third derivative you're talking about. Okay, to find the third derivative of our original function, we take the derivative of the second derivative. So that's 2 times, bringing down the power negative 3 as the coefficient, and then subtracting 1 to get negative 4. That's negative 6 x to the negative 4. And then the fourth order derivative of our original function is negative 6 times negative 4 x to the negative 5th. So that would be 24 x to the negative 5th. Let's just rewrite it. Let's use fractions again. So this would be 24 over x to the 5th. And we like to write it using the notation given in the beginning. So even though we were using exponents throughout the work, we're going to use fractions to represent our answer because it was given to us as a fraction for the question. So we write our answer using a fraction as well. One of the biggest applications of the derivative and the second derivative in real life are the functions that are represented by the position function, the velocity function, and the acceleration function. If we have a position function given by s of t, where s is in a distance and t measures how much time has passed, then our velocity function, v of t, can be found by taking the derivative of the position function. Notice that over here we just have the derivative written out as the limit of the difference quotient using s of t as our basic function. And then if we decide we want to take the derivative of the velocity, then we find acceleration. Acceleration is the rate at which velocity changes. So acceleration is the first derivative of the velocity function, which would make it the second derivative of the position function. And notice that all of these have the same variable. So t will still be measuring time, but then each of these measures a different unit. This would be the distance at a given time, this would be the speed at a given time, and this would be the acceleration at a given time. We're given a function s of t is equal to 10t squared, and then we're asked to find the velocity function and the acceleration function. After we find both of those functions, then they ask us to evaluate the distance, the velocity, and the acceleration when t equals 4 hours. Let's start off by finding the functions to begin with. Given that s of t is 10t squared, my velocity function will be the derivative of the position function, and so that's going to be 10 times 2t to the power of 1, or 20t. And then we have my acceleration function is going to be the derivative of the velocity function, so then that's going to be just 20. So these are my three functions. Then it asks me to find the distance at 4 hours, so s of 4. So we would be 160 miles from our starting point. Then the velocity at 4 hours would be 80. What's the unit for velocity? That's the derivative of speed. So if we were thinking about the notation, it would be the change in y over the change in x. So that's going to be the change in miles in the change in hours. Another way of writing this is 80 miles per hour. And then the acceleration at 4 hours would just be 20. Notice that there's no variable in here, so I have nowhere to plug that in. And that 20 would be the change in miles over the change in hours squared, because we took the derivative with respect to x a second time. We typically write this 20 miles per hour squared. So there we go. We found our velocity function, we found our acceleration function, and we found the position at 4 hours was 160 miles. The velocity at 4 hours was 80 miles per hour, and the acceleration at 4 hours was 20 miles per hour squared. Video example 5 says that a pebble is dropped from a hot air balloon. Find out how far it has fallen, how fast it is falling, and its acceleration after 3.5 seconds. So it gives us a position function. It says let s of t be 16t squared, where t is in seconds and s is in feet. Let's just translate what this question is asking us. When it says find out how far it has fallen, that's find its position, or the s function. Find out how fast it is falling, that's its velocity. And then find its acceleration, which is already labeled as acceleration. And so we need to find these functions first, and then we're going to plug in 3.5. The position function is already given to us. The velocity function is the derivative of the position function. So that would be 16 times 2t to the power of 1, or 32t. And then the acceleration function is the derivative of the velocity function. It's the second derivative of the position function, and the derivative of 32t is just 32. Now let's go ahead and plug in 3.5 seconds to each of our functions. So s of 3.5 is 16 times 3.5 squared. And my calculator tells me that's 196. And let's look at the units. The units is in feet. So that's 196 feet it has fallen. The velocity at 3.5 seconds, let's plug that into our function. We get 32 times 3.5. And my calculator gave me 112. And my units is going to be feet per second. Once again, that's my change in feet over my change in seconds. Because the velocity function is the derivative of s, we could also have written it ds dt, which tells us that it should be the feet over second. And then our acceleration at 3.5 seconds is 32. And because I could have written that as d dt squared of s, then that's going to be feet per second squared. All right. So hopefully looking at the Leibniz notation helps us figure out the units. And then that helps us solve questions like this where we have derivatives and second derivatives and speed, velocity, and acceleration. Thank you. Have a good day.